Hi, folks. Chris McClure. It is Friday, June 6th, and we are going to start a new chapter, chapter 4, today. And we're going to first look back and where we have been and where we've come from. We've been talking about going and collecting some data in the form of a sample from a population. And then we characterize that data by, figuring out what is the distribution. We characterize that distribution by finding maybe some measure of central tendency, like the mean, and some measure of variation by, say, calculating the standard deviation. Or maybe we construct a box plot. So in other words, we are trying to understand the distribution of the sample so that we can eventually say something intelligent about the population as a whole. Now, what we're going to talk about in this chapter is probability theory. And we're going to come across this ideal of the rare event rule for inferential statistics, which basically means that if we are making an assumption and then we calculate the probability of some sort of outcome, and under the assumption that we made, the probability of an outcome is small, then that calls into question the assumption that we had made. So, for example, if we have this mysterious coin and somebody wants to play a flipping game with money involved, so doing some gambling, well, I tell you what, if I were you, I would be wanting to decide whether that coin is a fair coin. A fair coin is one in which each side is equally likely to come up. A heads is just as likely as a tail, 50-50. So if we go under the assumption that it is a fair coin, and then we flip the coin, say, 100 times, and only, say, 11 heads comes up and 89 tails comes up. Now, I'll show you in a later class how to calculate the probability of that. But it really is a rather small probability of getting only 11 heads and 89 tails if that really was a fair coin. Way less than a 5% probability. So we would probably come to the conclusion that the assumption that that coin is a fair coin is probably not right. So that's an example of the rare event rule. All right, so we're going to now move on to section 4.2, where we're going to cover some basic ideas of probability, and then this is going to set the scene for more advanced discussions of probability later in this chapter. All right, some basic ideas of probability. We're going to talk about what is probability and how to interpret probability values. Now, we need to get some definitions under our belt in order to have an intelligent discussion of probability. The first piece of language here is the event. An event is nothing more than some collection of possible outcomes from an experiment. So if you take a look at the set of all possible outcomes of some sort of procedure or experiment, then an event is going to be one or more of those outcomes. It could be all of them, it could be one of them, or even none of them, but it's going to be some combination, some subset of all the possible outcomes that are that could arise from the experiment. Now, a simple event is an event that cannot be broken down into simpler components versus a more complicated event that could be the union of two or more events. when we talk about a sample space, we're talking about the set of all possible simple events, otherwise known as outcomes. Okay, so for example, if you want to think about rolling a single die, well, and you want to observe the number that comes up, then the sample space will be 1, 2, 3, 4, 5, 6. Because those are the 6 possible outcomes. Let's take a look at another couple of examples here. Suppose that we are going to talk about births of babies, and each time a baby is born, we observe the gender of the baby. Now, if we are looking at a single birth, then it's possible to have a boy or a girl. So a boy, comma, girl would be the sample space using this notation right here, using the set sort of notation. An event slash outcome here would be having one girl. Now, in the experiment slash procedure of having 3 births, maybe you have 3 mothers, they're in the maternity ward of the hospital, and you're going to observe, the genders of the next 3 babies born. It could be that you have 3 boys, boy, boy, girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. So these are the 8 outcomes that are possible if the order in which those genders are born is important. And an example of an event would be having 2 boys and a girl. That would be an event. Boy, boy, girl would be one outcome in that event. Boy, girl, boy would be another outcome in that same event. And girl, boy, boy is yet another way of having 2 boys and 1 girl. So the event of having 2 boys and a girl consists of these 3 possible outcomes. And this event, 2 boys and a girl, is a subset of the sample space. Okay, an event is always a subset of the sample space. Some notation here. P stands for probability, typically. When we use other capital letters of the alphabet, like A, B, and C, maybe E and F, those are usually going to be names of events, because an event is really a set. And we typically give sets in mathematics the names of letters. So when we see P of A, just like in functional notation from algebra class, this means the probability of event A occurring. Now, there's going to be 3 different ways that we're going to talk about of how to determine, how to calculate the probability of an event. The first way that we're going to talk about is the relative frequency approximation of, probability. Okay, this is where you're going to take a look at some data, and then based on your experiment and the data from your experiment, then you can calculate experimental wise what is the probability of an event happening. And what you do is you count the number of times that event A happens divided by the total number of times that your procedure was repeated. So, for example, suppose that we want to calculate the probability of a head coming up for a coin. Well, what we could do is flip the coin 1,000 times, and of those 1,000 times, suppose that 111 heads came up. So you take 111 divided by 1,000. That would be 0.11 or 11.1%. And that would be the probability of getting ahead. Or suppose in basketball that you have made, 50 of the last 100 free throws. So that means that the probability of you getting a free throw next time is going to be 50%. Now here's the classical / theoretical approach to calculating probability. This requires equally likely outcomes, okay? And what we do is to calculate the probability of an event A is we count the number of ways that the event could happen divided by the number of different simple events. In other words, the number of ways that event could have happened. So for example, suppose that we want to calculate the probability of rolling an odd number when we roll a die. And it's a fair die, meaning each side is equally likely to come up. So the probability of rolling a fair die will be 3 out of 6, because there are 3 odd numbers that are possible, 1, 3, and 5, and there are 6 different possible outcomes from rolling the die, so you'd have 3 divided by 6. In other words, 1/2, or 0.5, or 50%, would be the probability of rolling an odd number. And then there's the subjective probabilities. We do this sort of thing every day in judging as to whether or not we should drive our car, step outside, or anything like that. We have to subjectively judge the likelihood of something happening by using our perception of the relative circumstances. So the probability of me getting rained on while I'm out running can be judged by looking at the dark clouds to the west, and maybe you can smell moisture in the air. And oh, by the way, you can look at the radar. And then you can get your subjective probability of getting rained on when you run. So regardless of how you calculate your probability, we have to contend with the law of large numbers in our life, which kind of makes the connection between the fraction of times that an outcome results in your desired event versus the probability of the event in the first place. So for example, if we want to calculate the probability of getting an odd number when we roll a die, we saw that was 1/2, right? Or 50%. Well, if we were to take that fair die and start rolling it, and we keep track of whether we get an odd number or not, and we're keeping the good score as we roll the die, and we're doing it a whole bunch of times, and what we are going to observe is the more or often that we have rolled the die, the greater that fraction of times that the die comes up an odd number is going to be to 1/2. And as we get into the millions and billions of rolls of the die, the fraction of times that it comes up an odd number will get closer and closer to 50%. Just like if we were to roll a die many billions of times, the fraction of times that it comes up a 1 or any other number, is going to get closer and closer to 1/6, because 1/6 is the individual probability of rolling a 1. Probability of getting a head in a single coin flip with a fair coin is theoretically 1/2. And if we were to flip that coin several billion times, the fraction of times that it comes up ahead will get closer and closer and closer to 1/2. Both of those are examples of the law of large numbers. Here's another calculation of probability. Suppose that we have 3 children and we keep track of the genders as the babies are born. There are 8 possible outcomes of having boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. And when we say girl, boy, boy, for example, that means that a girl was first, followed by a boy, and then a boy was the last child born. Okay. So anyway, so this first one you have 3 boys. These next couple, well, actually, this one you have 2 boys. And the next one you have 2 boys. 2 girls, 2 boys, 2 girls, 2 girls, 3 girls. So those 3, there are 3 ways of having 3 girls. There are 3 ways of having 3 boys. There's 1 way of having 3 boys, 1 way of having 3 girls. There's 2 ways of having children of the same gender. So to calculate the probability of getting 3 children of the same gender, well, there are 2 ways of that happening, 3 girls and 3 boys, so there would be 2 ways out of 8 possible ways of having 3 children. So there is a 1/4 chance when you have 3 children that those 3 children will be of the same gender. That's how you can calculate the theoretical probability of having, when you have 3 children, that they're of the same gender. Well, unfortunately, probabilities are not always easy to calculate. Or we might be able to calculate a theoretical probability, but we may have to do some work to try to match experimental probability with theoretical. And that's where computer simulations come in. And that's more of a computer programming thing. We're not going to talk a whole lot about computer simulations, but I could write a computer simulation of the roll of a die. And I could show you that the overall fraction of ones that come up gets closer and closer to 1/6. That'd be a great simulation to do. Or I could do a card drawing simulation where I have a virtual deck of 52 cards. So I can simulate the drawing of 5 cards for a poker hand. Regardless. So we use simulation and statistics a lot. Not a whole lot for this class, though. Some things that we need to know about probability. Probability is a number between 0 and 1, which measures the likelihood of an event happening, with 0 being that it's impossible, and 1 probability of 1 means that the event is definitely, without any doubt, going to happen. It is certain. And then for any other event that is not impossible but not certain, the probability of it is between 0 and 1. So for any event A, the probabilities between 0 and 1. It does not make sense for a probability to be greater than 1 or to be less than 0. You can kind of think about this sliding scale for the probability of an event, with 0 being impossible, 1 being certain. Probability of 0.5 means it's like a fair coin toss. It's just as likely to happen as to not happen. Between 0.5 and 1, it's more likely than not going to happen. Of course, with that probability getting closer and closer to 1, the more likely it is to happen. And on the other side here, with the probability being less than 0.5, it's less likely to happen, and then less likely. And the closer you are to 0, the less likely it is to happen. Sometimes it's easier to calculate the probability of an event not happening. And when we say that an event doesn't happen, we are actually taking the complement of that event. And here's the notation for it, A complement. It's just the letter A with a little bar over the top. It just consists of all the outcomes in the sample space that are not contained in our event. So, for example, the complement of rolling an odd number is rolling an even number. Or the complement of flipping the heads is flipping the tails. The complement of drawing a spade, when you draw a card from the 52 card deck of cards, the complement of drawing a spade is that you draw either a diamond, a heart, or a club. Suppose that we were to randomly sample 1,010 U.S. adults and ask them whether they smoke or not. And suppose that 202 of them said yes, that they were smokers. So the experimental probability of having a smoker then is about 0.2, because 202 divided by 1,010 is 0.200. It's actually exactly equal to 1/5. So the probability of there not being a smoker, so meaning if you were to randomly select someone from that sample, the probability that he or she is not a smoker is going to be 1 minus 0.2, which is 0.8. Because the probability of an event plus the probability of the complement of the event together must be equal to 1. So if you know the probability of an event, you can subtract from 1 to get the probability that the event doesn't happen, or vice versa. Sometimes it's easier to calculate the probability of the event not happening than subtract from 1 in order to get the probability of the event does happen. So we're going to use that from time to time in the future. Just a quick word regarding how we express the results of our calculation of probability. Now, whenever possible, try to write a nice, easy fraction like you see here. But if it's a more complicated fraction, then just express it as a decimal. And if you're going to write it as decimal, just round it off to 3 decimal places. We talked in the previous chapter about what it means for an event to be unusual. And we said that if an event is outside of that, mean plus or minus 2 standard deviations set of bounds, then that's unlikely. Well, as we will see in the future, that for most distributions, the probability of an observation being greater than the mean plus 2 standard deviations or the mean minus 2 standard deviations, less than that, is going to be 0.05 or less. And that matches this first statement up here that says that an event is said to be unlikely if its probability is really small, as in 0.05 or less. And if you had a fair coin and you flip your coin 1,000 times, the probability of getting 111 heads is really small, because we expect to get closer to 500 heads out of 1,000 coin flips. And I'm pretty sure that the probability of getting 111 heads or less is much less than 0.05. So there were an unusually low number of outcomes. If we were, instead of getting 111 heads, we were to get 937 heads, that would be an unusually high number of outcomes. In other words, when you have such a large deviation from the number that's expected under the assumption, then we would say that that outcome is unusual or unlikely. So we've talked a little bit about probability. Now, the cousin of probability is odds. Now, remember, probability is a number between 0 and 1. When we talk about odds, odds are expressed as a ratio. Now, when we talk about the odds against some event happening, what we are talking about is the ratio of the event not happening to the probability that the event does happen, expressed as ratio, A to B. And you would just simplify this ratio to where you just have a ratio of two integers having no common factors. Like, there are 3 to 5 odds against that horse winning the race. You could turn that around, turn those numbers around for the odds against to express the odds in favor of. The odds in favor of an event happening is going to be the ratio of the probability for the event happening to the event not happening. Okay? So like I said, it'll be the reciprocal of the odds against. So if it's true that the odds against that horse winning are 3 to 5, that means the odds in favor of the horse winning are 5 to 3. Think about it. If I say that there's 5 to 3 odds in favor of the horse winning, that means if we were to run the race 8 times, then we would expect that horse to win 5 of the times and lose 3 of the times. Now, when we see the word or the term payoff odds against an event happening, that means the ratio of the net profit to the amount bet. So that's the payoff odds against your event happening. So that's the ratio of net profit to amount bet. So if you know any 2 of the 3, then you can solve for the third, as we will see in this example here. So suppose that we're going to play roulette. Remember that roulette has 38 slots. And there's 18 of one color, there's 18 of another color, and then there's 2 of a third color. Now 13 is one of the main colors. And if you place a bet on a specific number, there's a 1 in 38 chance of that roulette wheel landing on your number. Now let's suppose that we bet $5. Now we're told that the payoff odds are 35 to 1. So we have some questions to answer. seeing this dollar amount bet, knowing the probability of winning, and knowing what the payoff odds are. So here's some questions. Find the actual odds against the outcome of 13, and also, for part B, how much net profit would you make if you win by betting on 13? So let's tackle that first part of the question. Find the actual odds against the outcome of 13. Now, the probability of not winning, meaning the probability that the roulette wheel does not land on 13, is going to be 37 out of the 38 possible numbers it lands on. So there's 37/38 probability that this person will not win. And there's a 1/38 probability of winning. So to calculate the actual odds against winning will be the probability of not winning divided by the probability of winning. And that simplifies to 37, as in 37 over 1, as in the ratio of 37 to 1. So the actual odds against winning are 37 to 1, expressed as that ratio. Calculate the probability, or actually to calculate the profit. Now we're told that there are 35 to 1 odds. We bet $5. So that means what? That means if you win, you will win 5 times 35, which is $175 net profit. Means that $5 that you paid for your ante, you'll get that back plus the $175 profit, for a total of $180. So to calculate how much money that you would get in net profit, you would take the dollar amount that you bet times the payoff odds. Okay? So with that, we are done for today. We will continue talking about probability next week when we get back, okay? So have a good day, folks. Have a good weekend. I'll post some homework for you. And I'll talk with you next time. There we go.